So today we welcome co-director of Semiconductor Degree Program at Purdue University, Dave Jens, to talk about next steps in semiconductor at Purdue.
Thank you, and glad to see you all again. I was here at the beginning of the semester to give you a brief overview of what kind of the industry looked like and all that. And hopefully you've enjoyed hearing from people in industry. As you're aware, we rely strongly on our industry partners, both for support of our programs, but also to help guide us. We just had a leadership board meeting in Indianapolis a few weeks ago, brought together again some of our key industry partners to help us understand where we're going. We sort of present to them some of the information you'll see here actually today, but others. So I wanted to give you a brief overview of what to do next. Supposing this got you interested in semiconductors or let you learn that your discipline is actually quite important to the semiconductor industry. I'm going to give you a brief overview of some opportunities, but then we have representatives from various programs, students, a little bit senior to you, but students nonetheless, who can tell you what it's really all about instead of hearing me talk about it. So you're probably aware we have a very extensive semiconductor degrees program at Purdue. We started in 2022. It's one of the first. We used to claim the first comprehensive semiconductor degree program in the U.S. One or two of our university partners pushed back a little bit, like, wait a minute, we have semiconductor degree programs too, so now we claim one of the first. We don't want to get in those turf fights. But the broad goal is really to attract students into this field. You're here because you're interested and want to learn more about it. Train students for careers in the semiconductor industry. We try to cut across all the sectors of industry, which you've heard about over the course of this semester. You now know what all those are and what they do. And certainly disciplines all across engineering and beyond. There's multiple pathways in the program that I want to talk more broadly about today, so I won't spend a whole lot of time on this slide. But you've already been through the first step. This is actually a slide I showed to our leadership board. You're in Changing the World with Chips. You're part of the 720 students who have now gone through that program over the last 3 years or so. As you're aware, we split it this year, so we had both semesters, and we now have students from our Indianapolis campus participating, so that's growing pretty radically. You've certainly heard over the course of the semester about Moore's Law, this constant scaling of the semiconductor industry. We've been through a Moore's Law of student participation over the last 2.5 years. It's kind of interesting. When you can impress the industry people with how fast you're growing, you know you've done something. The STAR Summer Internship, which I assume many of you applied for, let me just tell you up front, we had 860 applicants this year for about 70 seats. So most of you who applied are not going to be able to make it into STARS, but one of the take-home messages from today is that the STARS Summer Internship is not the beginning or ending of your semiconductor career. There's lots and lots of other opportunities which quite frankly match you up much better with industry to go get an internship, say next summer, things like that. So that's what today's all about. STARS is not the stamp of approval that you are a semiconductor person or you're not a semiconductor person. It's a wonderful program, wonderful experience, but it's just not the thing we can have everybody in the room or everybody who applied participate in. If you did not get in, does not say anything about your quality of your character or your technical accomplishments. As a matter of fact, if you've already had several of the courses related to STARS, we probably said, no, you've already done the courses, go get a real internship at this point. So don't read anything into that, okay? So I want to talk about some opportunities where you can continue on assuming that this class has whetted your interest or generally you've become interested in this field, how can you continue on during the rest of your time at Purdue and beyond? And really a few broad things. Experiential learning programs, which we've invested in very heavily at Purdue, and that's where we get a lot of good corporate sponsorship, corporate leadership and interest. We have internships. Sophie's day job is to actually help place students in internships in these fields. Courses and certificates, concentrations, and minors, as you've already heard a little bit about. So here's the chart we show to our industry board. You're one of the 29,000 students in STEM fields at Purdue right now. As you're all aware, we've grown radically. Those of you trying to get a dorm room this year or trying to find an apartment for next year know that this place is really jammed. We've grown a lot over the last few years. But across engineering, science, polytech, and we partner strongly with Ivy Tech, our statewide community college. Of all those people coming in, we have about 3,000 students a year that take at least one semiconductor-focused course. We have about 100 semiconductor-focused courses. And so odds are many of you will take at least one of those courses over your next few years at Purdue. we move on, as already been said, we have certificates, concentrations, and minors. I'll talk a little bit about what those mean. But all the rings on here actually are stages of program. You're already in the first one, the Changing the World with Chips course. We have the STARS Summer Internship, which we're now broadening into a sustained training and readiness activity to take you through 4 years while you're here. We have, as I mentioned, over 100 semiconductor-related courses that cut across most departments in engineering, plus management and other related departments on campus. We have everything else on here that I've labeled is really what we call experiential learning. Project-based courses, internships, study abroad. As a matter of fact, moving toward the campus-wide certificate, you can count things like a study abroad opportunity in semiconductors. You can count things like a corporate internship. So all those things count toward developing your certificate program. So, as I mentioned, we have 100 plus courses that are related to semiconductors. They cut across engineering. They include things like supply chain. So there's lots of interest in that. Many of those you'll be taking as part of your engineering disciplines anyhow. I think most of you have probably just recently gotten into a major, and as you go along, I'm sure you've heard this semester there's opportunities for almost every engineering major to participate. As I mentioned, we have a university-wide certificate. It involves getting credit for things like the experiential learning programs. We have study abroad opportunities, the corporate internships, and then you take some of the 100 semiconductor courses. We also have departmental concentrations and minors. So as you go through your major, most of you have probably started looking at it now. There's some number of required courses. There's some number of sort of, what do we call the tech electives? Tech selectives nowadays, things like that. As you start looking at that, note that we already have departmental concentrations. So if you want to do a concentration in semiconductors and microelectronics, those are already in place in ECE, ME, and MSE. IE has got a well-defined draft. They're going to get approved in the near future, and chemical engineering is also working on a concentration. And you can do both. You can get the campus-wide certificate and the departmental concentration. Doesn't cost any more, doesn't cost any more tuition to do that, other than just if you stay on an extra semester, you probably have to pay some extra tuition. But double dip, get both of those, and you can get both a campus-wide certificate and a departmental concentration. I mentioned the 100 or so semiconductor courses. Here's at least my quick list of some of the departments those span across. So lots of opportunities for you to take semiconductor relevant courses that help build your expertise, get you ready to go get a corporate internship and eventually a job in industry, or stay on for grad school someplace. So I think there's lots of opportunities to do that. Any questions so far? Anybody have anything on their mind from today or the whole semester? But just thinking about finals. Get that project done, finish up for the semester. The weather's getting nice, but you got to buckle down and study. Okay, so the STARS, a number of you probably applied. How many people in here applied for STARS, by the way? Maybe I should ask who didn't apply for STARS, right? Okay, great. I wish we could have gotten you all in. I think you all would have been well qualified. You're all interested. You've all heard about what's going on in industry. So STARS is a program we spooled up a few years ago. Its original title was Summer Training and Readiness in Semiconductors. It's a summer 8-week or so internship. The reason we can't scale it to accommodate everybody who's interested is these are paid internships. Companies give us money to sponsor paid internships. And we're already getting pretty generous sponsorship. Some of the lead sponsors are already putting in 10 slots per year and things like that. So it's really difficult to say, okay, we can get everybody in the room involved in that, given the program costs and associated work required. As I've already said, though, it's not a prerequisite for anything else we do. Nothing in that progression toward a certificate of concentration, a corporate internship, really relies on STARS. So don't think of it as that stamp of approval that you're a semiconductor person or not. The real pipelines to companies, if you want to get internships and jobs, run through the things we're going to talk about with the student presenters today. The VIP teams, the scale program, your classes, your certificates, those are the pathways to get you ready to go for a career in the semiconductor industry and to get you that internship or job. I had this big complex chart I'd made that everybody tells me I shouldn't show because it's too complex, but you can really see these pathways. Students come in and start taking VIP projects or start taking coursework. They go off and do company internships. They come back and now they're of great value to their teams on campus. We're starting to see companies that say, hey, we want to hire more of your students that have been through these experiential learning programs. So there's a lot of interest and a lot of things going on there. So we're really morphing it at this point to where STARS will still be a name, a brand, a logo, but really it's going to go beyond summer. It's going to be sustained training and readiness in semiconductors, where we're going to pay attention to how to get you into these pathways so that instead of just taking all of your standard departmental courses for the next 3 years, you'll actually have an opportunity to do some things very semiconductor relevant and related. So one of them that's already in place is there's an intro to socket. If you're interested in chip design, there's already a intro to socket program. It's a 2-semester course sequence that gets you ready to join a socket chip design team. Those socket design teams do tape outs to actually have chips fabricated at external foundries approximately twice a year. And so there's already these programs. I believe there is an on-campus section and it will be resume again in the fall. So if you're interested in chip design, a great way to get into it is the intro to socket, then join a socket team. We are spinning up we're tentatively titling it STARS Academic. It's an intro to semiconductor processing. This is also aimed at getting you ready if you want to join a VIP at Birck team doing manufacturing or packaging. So we're starting this summer in a NanoHub course, and we hope to turn it into a credit-bearing Purdue course by next year. And so this is great introductory material, whether you want to join an experiential learning program on campus or just learn about how device processing and packaging works. We'll talk about some of the unit process fabrication skills. A lot of things you heard this semester, people were like, oh yeah, we're integrating this and this and this. And you're probably there like, okay, what was all that? But this is a chance to learn what all those unit process steps are. What did they mean by silicon epi and etching and doping and regrowth and vias and contacts and all these things they were talking about? This is a chance to see some of that. Some of the lithography that you've learned about, some basic chances to understand some fundamentals of all that. So I highly recommend looking at these things. We'll post a link on the course webpage so you can know where it is on NanoHub, but these are great experiences to get started with. So again, we're broadening it out. We understand we're limited with the internship, but we certainly make some of these other opportunities available. Internships are quite important. Companies are quite interested in students coming for internships. There's also still the co-op program if you want to do multiple semesters at a given company. The disciplines vary by sector. I think you've seen in this semester a lot of different companies hire students from a lot of different disciplines, but it's different. If you go into the chip design, the fabless chip design companies, it's a different set of skills or a different set of backgrounds and disciplines than if you go into, say, a foundry, a materials company, a tool manufacturer. Those are all different sets of disciplines and skills. And I think you've had a chance to see this semester some of the exquisite, say, mechanical engineering that goes into these systems, the industrial and chemical engineering that underpins all these processes, so it's really important. So for resources, you've got the Office of Professional Practice, where, as I mentioned, Sophie sits, and they certainly can help connect you with these things. We have SCALE, which is largely a defense and aerospace-focused program, but they have their own placement office, their own internship opportunities. And starting this fall, there will be a semiconductor-focused career fair. You probably, last fall, were aware of the Industrial Roundtable, which is a campus-wide general career fair. The semiconductor industry was sort of asking us if we could have a more focused career fair where you would be able to talk specifically to people in the semiconductor industry. So starting this fall, we will have that. So that's coming on the way. I mentioned our corporate sponsors, corporate participants. This is our Semiconductor Degrees Leadership Board. There's 40 companies on here. They span the industry, what you would know about. We have foundries, we have fabless design companies, we have tools manufacturers, we have materials companies, we have the CAD, the design tools, the EDA design tools segment illustrated here. And so this is the advisory board. We have people that are pretty senior level that advise us, people at kind of the CTO, VP level. So it's quite it's a hard board to keep up with. They ask some tough questions of us. So as you go forward, one of the opportunities is international experiences. So we have international partnerships, and over the last couple of years, we've had 1 or 2 study abroad opportunities, usually a few-week faculty-led opportunity. We've gone to places like Belgium, South Korea, Japan, not South Korea. Okay, that's coming up. Okay. And those are great opportunities to participate in. We also have a Silicon Valley trip every year. Silicon Valley is not exactly international, but it's a great experience to go out to where the foundation of the industry is and intersect with companies on that. This is my last, kind of my last slide before we go to the student presentations. But we have tons of courses and programs you can get involved with. The STAR Summer Internship is just one of them. As I mentioned, that's morphing now into a more sustained activity over the course of several years. But really what we have is opportunities where you can join multiple semester team projects. So we have this framework called vertically integrated projects. Anybody ever gotten on a VIP team, by the way? There's some freshmen, their first year engineering, yeah. So it's actually a program created at Purdue, but it's now 50 or so universities around the world that have these kind of programs. And it's a chance to, each project runs for multiple semesters, and you can participate over multiple semesters on a team. So it's a chance to do something substantial instead of just a little project within one course. You can actually do something substantial over multiple semesters. And it can count as a senior design option in many departments. So you can actually use this as your senior design project as you move forward. There's two semiconductor-focused ones. One's called Socket, System on Chip Extension Technologies, and we have a couple of representatives there who are going to tell you about that. We have VIP at Birck, which is a manufacturing and advanced packaging. The Birck Nano Center is our microfabrication and packaging facility on campus. It's on the diametrically opposite end of the campus in Discovery Park. Discovery Park. We have individual research projects that you can sign up and work with individual faculty on. And we have the SCALE network, which is a 33 university network. It's primarily focused on defense sector and commercial leap-ahead technologies. And as such, until recently, it was kind of restricted to US citizens. My understanding is they're going to broaden that. So even if you're not a US citizen, there will probably be opportunities to get involved. And I have a couple of overview slides. We did have a video presentation on this, but the format's not working, so I think I'll just give a couple slides after we hear from everybody else. And then we have the Semiconductor Student Alliance, which is a great sort of hub and resource to coordinate and provide information. So let me turn it over there, please. And we'll hear about SSA. We can just set up a second here. That's not it. Where'd it go? There it is. It should be live.
Hello, everyone.
Is this working? Yeah.
But is that the...
I'm Zara, and a marketing officer in SSA. I'm going to introduce you to SSA. So our mission is to promote...
Sorry.
All right. Yeah, so our mission is to promote semiconductor programs and initiatives. So why to join SSA? We offer opportunities to improve your overall experience in semiconductors. We try to connect you with industry leaders. And we try to connect you with industry leaders. And in the past, we had sessions like with Marvell Technology, Texas Instruments, ASML, AMD, Intel, and more. You will also learn about research through conferences where you could present your research and learn from other students' research. We try to do networking activities so that you could meet the students who share same interests in semiconductors and learn from their experiences and how they got their internships. We have leadership opportunities in our committees too, so I highly encourage you to join us. And in the next slide, we have our QR codes. All right. Yeah, so I highly encourage you to scan these QR codes so that you will learn more about SSA and our activities. Thanks for listening, and if you have any question, you could send us an email to ssa@purdue.edu. Thank you. So I'll have this one.
Hello, my name is Matthew, and I'm here to help present on Socket, which you already saw as System on Chip Extension Technologies. There are a bunch of ways to get involved and a bunch of different groups that we have within it. I'm on one of the groups that falls under that third bullet point, which is used as a platform for other projects and research. I'm actually over at Birck Nanotechnology Center working with one of the professors there on a project for MRAM, or magno-resistive random access memory. I joined Socket as a junior, and I'm now in my second year, turning it into my senior design project. It's funny that Dr. Janes spoke at length about stars because it was actually in a Socket meeting where Dr. Johnson got up and said that he needed some more TAs for the summer. And I had just finished the 400 level digital design class at the time, so it was a right place, right time, perfect opportunity. Of course, there are different types of student involvement in terms of what you can put on your course load, but it's a wonderful way to get experiences with projects that are actually in the CE, EE, or entire ECE umbrella. This slide serves as a good segue into, I'd say, the largest flagship project of Socket, which is the AFTX, which is an example of our SoC, where we work mainly on the CPU, but the digital design team has many different little projects that they're always working on. So.
I'm Thomas Munson. Can y'all hear me in the back? Okay. Here are a few of our different chips that we've taped out so far. Socket has taped out, I think we're on to, have we taped out the 7 already?
I believe so.
Okay. So our first few AFTXO chips were just fairly simple CPUs. A couple of them had errors and didn't quite work right. But I believe the AFTXO4 was our first fully working CPU, right? No? Okay.
Too early for me.
The AFTXO5 came after, and we've been slowly adding on more new features, and even still, there are senior design teams who are adding new features to the AFTXO7 or features that will be added to the AFTXO8 once it is eventually taped out. So there's a wide variety of different technical topics or subgroups that you can join. This graphic here shows the design flow for a chip. So there are a few of our different sub-teams are the RTL team. They make the general high-level view of the code, or not code, but how the chip will be set up. Logically, how will it work? That's like a digital design. We have some custom teams, so custom digital, they make custom hardware versus standard cells, what the RTL team uses. We have analog teams, analog and mixed signals. I don't think they work on the AFTXO7 as much. We have verification teams to make sure that the AFTXO7 actually works and that when we get it back, we won't just get a rock. There's software, because if you have a CPU and you don't have software, you can't use it. Physical design verification, same as the verification team. PCB team and test engineering, so once we get the chip back, how do we actually use it and make sure it works? And we have a few other research collaborations. There are quite a few people on the AI acceleration teams and the GPU architecture team. We have a few people on MRAM and IP protection over at Birck. I believe you're on one of those. I work on the FPGA team. We design standard cells in that. And we also have another accelerator for signal identification as well. So there's a wide variety of topics that you can be involved with at Socket.
So if you are interested in getting any project experience, please maybe stop by. Even sit in on one of the lectures that they have weekly. They bring in people. It's a great time. But anyway, thank you very much for your attention.
So I just want to comment, these guys are pretty modest, but to do a chip design as an undergrad is pretty rare, right? I mean, if you look around the country, you would have to be in one of 10 or 15 universities around the country to even think about doing this. You can be an ECE student here and go through your 4 years of taking courses and never actually tape out a chip. These guys are doing it a couple times a year. So, I mean, this is really unique. Go compare notes with your friends once you're home for the summer, see if anybody else has this at their institutions, right? Okay. We have some students from VIP at Birck coming in a little bit. I don't think they're here yet, but we'll get a presentation on that in a few minutes if you're interested in fabrication or advanced packaging. We had a video from Scale, but it's not, the format got corrupted a little bit before it got to us. So I just want to give you a brief overview of the Scale Center. This is a, as I mentioned before, 33, I think somebody today said it's up to 35 universities. Every time I quote the number, it's grown a little bit. It was founded a few years ago by Professor Brumell and Professor Douglas, who spanned ECE and engineering education. And it's aimed at developing semiconductor workforce for defense and dual-use applications. As I mentioned before, it's in the past been fairly heavily U.S. citizen focused, but I think they are going to try to broaden that. So it's actually a national network. This shows you a lot of the sites, and it's listed at least some of the newest additions. I think if you look at the bottom, it tells you all the main institutions. But it's probably too small to read here, but they have several main focuses. They have focuses on embedded systems and trusted AI, on heterogeneous integration and advanced packaging, on radiation-hardened electronics, radio frequency and optoelectronics, and system on chip. And all those things together mean it's going way beyond just chip designers. There's lots of people from mechanical engineering, materials engineering, and other related fields focused here, because in order to do all these things, you really need to have innovations in materials, innovations in structures, and move forward on that. So the way it's set up, it's actually integrated with a local center called, or a regional center called Microelectronics Commons. So these are actually what they consider the tech verticals, so things we talked about before, plus they're working on AI hardware, secure edge, commercial leap-ahead technologies, and 5G, 6G cell phone technologies. So lots of opportunities to get involved. It's a unique program that involves faculty mentorship, internship opportunities, and first-time researcher opportunities. So you can get involved in lots of programs and activities. They are creating their own courses. So there's now a 500-level course, I believe is co-listed between ME and MSE on advanced packaging and heterogeneous integration. I'm getting the 10-minute warning, but okay, sure. Do we have the, you ready to go? Okay.
Hi everyone, I'm Alex. I'm glad to represent for Semiconductors at Birck to share with you the research that we've been going through as undergrads. Yeah, thank you. Hello, yep. So I would like to share with you the research structure, which we have integrated several times for past semester. And to begin with, we will have faculty mentors and Birck research engineers, which we'll work closely with because they are the ones that's really leading us and explaining the fundamental physics behind it. And so for faculty mentors, we have 4 professors, and we have many scientists that we work closely with. Whenever we have data, we want to discuss with them to understand what the data means and to know how to proceed. And for graduate teaching assistant, we usually only have 1, but she usually deals with all the coursework. So if you have any questions, you can ask him or her. And for student team lead, usually we have one per sub-team. So we have MIM capacitors, we have solar cell, I'm in the solar cell team. And we have for advanced packaging and heterogeneous integration, we have 4 teams, each working with one material. We have silicon, aluminum nitride, glass, and polymer. And what happens is the team lead will be the one that is guiding us because usually they are the most experienced and they have been working with at Birck Technology Center for a while now. So usually if you first go in, you'll be a junior student. And then after first semester, you'll be a senior student. And that's the structure so far. So I am technically a senior student, although I'm still a sophomore, because I've been working with semiconductors at Birck since last semester. And so if you're willing to join next semester, you'll start with junior student and you'll move your way up. And if you'll be a student team lead, possibly in the future, it'll be good for your resume because of leadership positions. And so this is the training process. So for working at Semiconductors at Birck program, it is a R&D center in a clean room. It will involve working with some dangerous chemicals, so we try to make sure that you are all properly trained to wear safety, gone up, gone down, and extra protection whenever you're working with, let's say, acid hoods. So in this case, if you're a new student, you would go through in-person training and then online training with quiz, and then you have lastly go through a clean room training where you will be taught with all the essential knowledge on how to protect yourself when you're working with chemicals. And for returning students, we will also go through a simplified process of training every semester. And all this just to make sure to keep you guys safe when doing research. So to begin with, this semester I'm in the solar cell project. And so I want to introduce my project to you guys. And if you're interested, feel free to shoot me a message if you want to join the team. So an overview is that why we choose solar cell. We can do many projects. We have metal insulator metal capacitors. We have APHI, but then the reason why I choose solar cell is because it is so closely related to other nanoelectronic components such as LED, transistors, etc. So that all the knowledge I learn here can apply to working with other nanoelectronic fabrications for future when working in the industry. And so the background knowledge is very important. Usually when you first started a new project, you would like to understand the fundamental physics or device physics behind it. So for me, I just break it down to you the simple physics for working with solar cells, such as band gaps, photogeneration. For this is not really important unless you're working with solar cell, but I think it's good to know the basics if you're interested in joining the future. Another important understanding is the structure of the solar cells. We work with one of the recipe from a Purdue professor, and then we integrate it several times from each of the results. So from here, you can see that there are 2 p-n junctions. And the second P++ region is to improve the efficiency of the photogeneration. And you can see on the top, there are solar cell patterns, which is when connected with the external circuit, you can guide the electrons or current through the external circuit back to the P++ region, and then through the depletion region, and then first generates voltage. And so for fabrication steps, it's actually over 50 steps. But to break it down, we begin with substrate preparation. It's very important because for solar cells or other complicated projects, work ethics is very important. You want to minimize contamination. Although we know that during R&D, contamination is inevitable, we still want to make sure to reduce contamination as much as possible because that's the biggest reason why our device might fail. So begin with, we have substrate preparation, cleaning, most importantly, with all sorts of cleaning. And then we begin with P++ contact formation, which is where the boron dopants are at. And then we move on to front side N plus contact with phosphorus, SOG. Spin on glass is one of the industry standards, very saturated method. And then we move on to lithography and metallization. Hopefully you guys understand lithography. That's where you use the photomask for interconnect patterning. We also use titanium and aluminum, titanium for adhesion, aluminum for main conductor, and to improve charge carrier concentration. We'll do the same on the back side because we want the external circuit to connect for a solar cell to function properly. And lastly, we'll do several measurement methods to really understand how our device is working. So IV curves and CV curves will be shown later. Essentially for IV curve, current voltage, it should be a smooth exponential curve. I will show several results we have over the few prototypes. And as you can see, we make progress improvement through each iteration. SCM is one of the tools that we really would like to use because we can essentially dice the device in half and to look at the depletion region, which we can see whether or not it is well formed, or is it a tight, or is it a wide depletion region. That helps us to understand whether or not we made mistakes in our fabrication process. So to break it down, it's over 50 steps. This is a little simplified, but of course, this will help you understand better. Start with removing all the oxide layers and then forming SOG boron for P++ until step 9, and then repeat the same process for the front side until step 13. That's when we have, oh, by the way, so for the substrate, it comes with factory set P type. So the P and the N already has a PN junction, but then the bottom P++ forms the second PN junction to improve efficiency. And then we'll do photolithography from 14 to 16. And then from 17, it will be metallization, where we'll have the solar cell patterns at step 18. And then we continue with from 19 to 21, which will be the back side metallization. And technically, by that time, we'll be done. But sometimes we will do annealing to shoot the dopants into the substrate so that it forms a better PN junction. So for the final design, it will look something like that. So here I would like to share the results. You don't have to read all of them. So as I mentioned, contamination is the biggest issue we have encountered so far. We tried several cleaning methods. We tried several photomasks. We try all ways to reduce contamination, because with contamination, there will be series resistance, which will, instead of a smooth exponential curve, it will be more like a resistor, which you'll see in the second prototype. As you can see, this is not as good as we expect. We do see the current decreasing linearly with increased light intensity, which shows that we have formed a PN junction. The device is working somewhat. However, there's such a high resistance such that the current cannot perform a smooth exponential curve, meaning that we need to try to solve this issue. So our method is to switch from piranha cleaning to plasma cleaning. We're switching our cleaning methods, trying to see if it cleans the contamination better, if it removes the oxide layer better. And then we'll also remove the RTA process at the end of the device fabrication, because I was worried that that could hurt the PN junction at the very end, and also double the aluminum deposition thickness, which is the solar cell pattern at the very top of our device. So for the third prototype, I'm glad to show yeah, absolutely. So this is a much better graph showing that smooth exponential curve, indicating that we have a functional device. And we still need to make prototypes for next run. And this will be our R&D focus and our fabrication focus. And we plan to also do documentations for all of our work so far. And if you're interested, feel free to send me an email if you're interested in joining solar cell team. I'll also quickly go through MIM project introduction. Okay, yeah. So this is my email. If you guys are interested, send me email if you want to join. And you can also find me after class. Thank you.
Okay, I'll turn it back over to Sophie here in a minute to wrap up. But I just wanted to thank you all for your participation and note, just as we said with Socket, the chip design team, as Alex just told you, we have the Birck Nano Center, which is one of the largest academic clean rooms in the country with lots of outside fabrication and characterization equipment. So it's a chance to get a unique experience there that you would not have at most universities in the country. But my advice is, get involved. Take advantage of these things that are there. Be on your courses, do well in your courses. There's no second guessing that. But when we talk to companies, they like to have students that say, I've been in a project, I did this. We had a luncheon a few months with one of your speakers, actually, from TSMC in Arizona. We had the president of TSMC Arizona here, and there was a lunch out at the Birck Center that day. And every student around the table was able to introduce themselves, say, I'm a sophomore in XYZ discipline, but then they could also say, I'm on a team that's doing this, and my specialization is this. And the people from TSMC, including one of their recruiters, was like, wow, this is really neat. Usually you talk to a student, they say, well, I'm a sophomore in mechanical engineering or something, and it's like, okay. But what they want to know is, what have you done, and how are you starting to think about this? How are you integrating these ideas? How are you understanding some component of the industry? They don't expect you to understand everything, but pay attention to getting these project experiences where you can really say, look, I am digging deeper into this aspect. Okay.